Our next speaker is Daniel Meyer from University of Liverpool. His talk is the title of the talk: Quasisymmetric Uniformization, Quasi-visual Approximations, and Thurston Maps.
Okay, thank you. So thank you so much for inviting me. Well, too bad that I cannot be there in person. And I mean, I don't know, for some reason, this is sort of like the worst week, because it's the first week of our term and the first week that I'm back in the classroom since almost 2 years. So it was really like, I would have really liked to be there in person, but okay. So yeah, so as I said, so this is a joint work with Meyer, Bonk and Mikhail Hlushchanka. I mean, I should say this is very much work in progress. And so, I mean, what we really are trying to do, we just have sort of, I mean, really figured out the first example. So, I mean, in a sense, this is more about, I mean, when we were kind of, you know, doing this, we sort of went back to some, in fact, quite old things. And I think, you know, the old things I sort of understand better now. So in a sense, it's really like reviewing old things in new light. Okay, so so let's see. Why does this not work? Just a second. Okay, I have some. Okay, all right. So I mean, I want to kind of promote this sort of idea that quasi-conformal geometry is the study of geometric properties that are invariant under scalings, okay? And so these properties, they involve relative distances, so ratios of distances. So for example, when we talk about, let's say, the derivative, we're taking ratios of distances, but we're taking the ratios of distances in the domain and in the range. Here, we just have ratios of distances in one given space, okay? And this is, you know, these are things that are good when you want to study things that are invariant under scaling. For example, like typical, you know, fractal objects, self-similar objects. And all right, so let's just give you two properties that are in this RAM. So the first thing is the doubling property, okay? So we have a metric space X and it's doubling. If so, okay, let's take a ball. So here's a ball, okay, and so now we can cover the ball with balls of half the radius, okay, and the number of balls is bounded by a uniform constant which we call n. It's a doubling constant, okay. So when we want to go to from a scale, let's say R to a scale R/2, we need at most capital N balls to do so. All right, and so typical examples, so Rn is doubling, and so the doubling property is inherited by subsets, so any subset of Rn is doubling. And typical non-examples is like infinite dimensional space, so like, let's say, infinite dimensional Banach space. Hyperbolic space is also not doubling because balls grow too large when the radius goes to infinity, okay? And the way we view the doubling property is that it's a property that is a finite dimensionality property. So you can make this sort of quantitative. So you ask how many balls you need if you, let's say, take balls of smaller and smaller radius, and then you look at the exponential growth and you cook up a dimension of this, and that is the Aswad dimension. And so the space is doubling if and only if this dimension is in fact finite. But really what I want to emphasize here, this is like a typical quasi-conformal geometric type of thing. So we only look at relative distances or relative sizes in the space. And so the other property is the bounded turning property. Okay, so we have a metric space and it is bounded turning if the following is true. So I take any 2 points in my space, X and Y, okay? And then I can find a continuum, let's say gamma, that contains my 2 points, X and Y, okay? And then the diameter of this continuum is not much bigger than the distance of the 2 points. So obviously, okay, so, this continuum contains the 2 points. So obviously it has to be, the diameter has to be bigger than the 2 points, but it's also not much bigger. And namely, so we have this uniform constant that bounds this here. Okay, so that's the bounded turning property. And again, what we are doing is we have relative distances. So we compare the diameter to the distance of these 2 points. Okay. All right, and so the natural type of maps in this context is these are quasi-symmetric maps. So I guess most people have seen this definition, but nevertheless, it's sort of a weird definition. So what does it do? Well, so we look at ratios of distances. So we have 3 points, x, y, and z. And so maybe I should have said this earlier. I mean, just this absolute value here. This is the Polish notation of the metric. So I guess in bed level, this is sort of okay to use the Polish notation. Okay, so we have these ratios of distances bounded by t, then in the image, so x prime, y prime, and z prime, these are the image points of my 3 points, okay? Then in the image, the ratio is bounded by eta of t, okay? So basically we have this function, usually it's said to be a homomorphism. That's not really important, but the point is that when t goes to 0, then eta of t goes to 0, and when t goes to infinity, eta of t goes to infinity. And so, you know, like if the ratio is bounded by t, then in the image is bounded by eta of t. And so the picture that you should have in mind is, so here is my point x, and here's my point y, and here's my point z. So, you know, like if we have, let's say, some blob, and then we look at the in radius, so the biggest disk around x that is contained in my blob, and we look at the out radius, the smallest disk around x that contains my blob, and then the ratio, we can think of this as the roundness of this blob, okay? And so basically we have blobs where the roundness is t, and then we map it over, and then we have the image points here, and then the roundness is bounded by eta of t, okay? So round objects are mapped to round objects in a controlled way. That's what a quasi-symmetry is. Okay, so maybe just real quick. So how does quasi-symmetry compare to quasi-conformality? I guess in this audience, people are more familiar with a quasi-conformality. So first of all, quasi-symmetry is a stronger property than quasi-conformality, so it implies quasi-conformality. However, if you have, let's say, a homomorphism of, let's say, Rn, I should have said here, n is bigger than 2. I mean, for homomorphism of, let's say, Rn, then quasi-symmetry is in fact exactly the same as quasi-conformality. But in a sort of, let's say, a philosophical sense, really, quasi-symmetry is a global property. So you don't have any limits in the definition, whereas I think of quasi-conformality as being an infinitesimal property. So if you think, you know, let's say that many definitions of quasi-conformality, let's say analytic definition, where you typically have a function that's in, you know, W1, 2, so we have some sort of weak derivatives. So it's an infinitesimal property. And so basically, quasi-symmetry is a global version of the infinitesimal property of quasi-conformality. And okay, so these maps originally come from complex analysis, right? So where do they come from? So if you have a quasi-conformal map of the upper half plane, then this has a quasi-symmetric extension to the real line, to the boundary. And in fact, this goes the other way around. So also if you have a quasi-symmetric map of the real line, then it has a quasi-conformal extension to the upper half plane. And so quasi-symmetric maps are used in metric spaces as analogs of conformalness. So, I mean, when you come from, let's say, the complex analysis world, then you know and love conformal maps. But of course, when we go to higher dimensions, there are very few conformal maps around. So, I mean, when we are in N, they're basically just all Möbius transformations. And if we are, let's say, in more abstract settings that say of metric spaces, there are very few conformal maps around. So conformal maps are just too restrictive in many settings, okay? And for this reason, then we use quasi-symmetry as a substitute for quasi-conformality. All right, and so maybe slightly more recently, quasi-symmetric maps, they appear in geometric group theory, and I don't want a group, so I guess it's a Fuchsian group. So it says my internet connection is unstable. I hope, can you guys still hear me? Yes, no?
Yes.
Oh, yes. Is my sound okay, or?
Yes.
Okay, all right. Okay, so so here we have you know, let's say well, Fuchsian group, and so here we have the Cayley graph, and then you know in a very natural way we can identify the boundary at infinity, which in this case would be the unit circle. And so if we, let's say, take a different different set of generators to draw our group, then you know the whole picture changes, and this induces in fact a quasi-symmetry on the boundary. But again, I don't want to give precise definitions here, but just that quasi-symmetry appear very natural in geometric group theory. All right, well, one thing I want to talk about is quasi-symmetric uniformization, okay? And so this is sort of, you know, the typical uniformization, you know, one of our, you know, let's say guiding theorems in certainly complex analysis. So, but here we have, let's say, instead of, I don't know, having the, let's say, a Riemann surface, or what we have a metric space, okay? And we ask, when is this metric space quasi-symmetrically equivalent to some model space? And maybe the most famous case of this is the question of when is a metric space that is a topological two-sphere. Okay, so we have a metric space, so that it's homeomorphic to the standard two-sphere. When is this a quasi-sphere, by which is meant that it is quasi-symmetrically equivalent to the standard two-sphere with, you know, the standard topology. Okay, and why is this important? And again, I don't want to give precise definitions here, but this question is closely related to Cannon's conjecture, which is, in my mind, the biggest open conjecture from Bill Thurston's work. So basically, it asks whether we can identify the fundamental group of a hyperbolic three-manifold by topological methods. Okay? But there is another equivalent formulation which asks whether certain spheres which appear as boundaries and infinities of certain hyperbolic groups, whether there are in fact quasi-spheres. So basically, you know, if you can solve this problem to identify a quasi-sphere, you can solve this important problem. And there's many people have done important work here, and I list a few. There's also a correspondence, and I will talk about this later in the talk, but I just mentioned this here already. There's Thurston's characterization of rational maps, and there is an equivalent way of expressing this in terms of that certain spheres are in fact quasi-spheres. But I will come back to this later in the talk. Okay, so how am I doing on time? Okay. And maybe another question that has received a lot of attention is, well, when is the Sierpinski carpet? Okay, so something that is homeomorphic to the standard Sierpinski carpet. When is this quasi-symmetric to a round carpet? And this is closely related to the Karpowicz-Kleiner conjecture, which is in fact closely related to Cannon's conjecture. So Cannon's conjecture in fact implies this. And so, I mean, let's say the quasi-symmetric properties of Sierpinski carpet, that has a lot of attention, and there has been some work, and I list some people here. Are there questions so far? Okay, so maybe I'll go, and so okay, so this is like the quasi-sphere problem, but maybe let me just first let you know what is known. Okay, and so okay, so let's talk about oops. Oh, come on. Okay, so we have a metric Jordan curve or Jordan arc. Okay, so it's homeomorphic to the unit circle or to just the unit interval. Okay, and so I mean, maybe like our guiding theorem of, like, I mean, let's say our ideal theorem that we would like for these quasi-symmetric uniformization results is this theorem. Jordan arc or Jordan curve is a quasi-circle or quasi-arc, meaning it's quasi-symmetrically equivalent to the unit circle or the unit interval, if and only if it is doubling and bounded turning. So we have some very simple geometric properties that are very easy to check, and that gives you, that it can be parametrized by a quasi-symmetry. There is another well-known characterization, which in fact is simpler than this, but it was proved much, much later by David Sampson. That's a characterization when something is a quasi-Cantor set. So a metric space is quasi-symmetrically to the standard middle third Cantor set that you all know, if and only if it is compact doubling, uniformly perfect, and uniformly disconnected. So how does that go? So basically you have the standard, let's say, topological characterization of a Cantor set, and you put in, I mean, instead of perfectness, you have uniformly perfectness, and in form of, instead of disconnectedness, you have uniformly disconnectedness. And I don't want to define these terms here, but if you sit down and think about how you would define them, that's exactly how you would define them. So basically, all, let's say the Cantor sets that come up in complex dynamics. So basically, let's say it's quadratic polynomials when my parameter C is outside of the Mandelbrot set. These are all quasi-symmetrically equivalent to the standard Cantor set. All right. So maybe let's say the two spheres that is very difficult, and we don't know a lot about the quasi-symmetric uniformization, and we know about arcs. So now the question is, okay, can we do something in between? That's sort of between like a two-sphere and an arc. And so I guess one thing to look at are trees. So what is a tree? So a tree is a compact, connected, locally collected metric space. Okay, such that if I have any 2 points, let's say here's a point X and here's a point Y, then there is a unique arc that connects these 2 points. I guess in topology, these are usually called dendrites, but for some reason, we prefer the term tree here. And okay, so of course, like for many polynomials, the Julia set is such a tree. So here is, I guess this is z squared plus I, and we have, let's say, attractors of certain iterated function system. One big motivation for us is actually comes from the random geometric world. So there's something called the continuum random tree, and that's a random metric space that is constructed in a very natural way from Brownian motion, but I don't want to define it in this talk. And all right, so remember from the Tucker-Weisler theorem. So an arc was a quasi-arc if and only if it was doubling and bounded turning. Okay, and so now we take a tree that is doubling and bounded turning, and we call such a tree a quasi-conformal tree. Okay, so it's doubling, has finite dimension, and it is bounded turning. So meaning if you take, let's say our 2 points in this space, and then this arc, the diameter, is comparable to the distance. So that's actually the same as to say that the arc between them is in fact a quasi. And okay, so maybe just a reminder. So a metric space, or maybe our tree, is a geodesic tree if this arc between them is in fact rectifiable, and the length of this arc is the distance between these 2 points. So, and if you have a geodesic tree, then it's automatically bounded turning, because the constant, the bounding turning constant is 1, obviously. And so here's our first result. Okay, so every quasi-conformal tree is in fact quasi-symmetrically equivalent to a geodesic tree. Okay, And so what does that mean? So that means if you have a tree, so you can straighten each arc in the tree simultaneously. So, like, well, one arc, of course, you can straighten. You could just use the Tokyo-Weisler theorem, but you can, you have, well, infinitely many arcs, and you can do this all simultaneously. Well, maybe here one thing to note is if you have an arc that is doubling and bounded turning, it's just an arc, okay, then this is a quasi-conformal tree according to our definition. And so our theorem then says that it's quasi-symmetrically equivalent to a geodesic tree, meaning it's quasi-symmetrically equivalent to just an interval. So that means our theorem, in fact, includes the Tokyo-Weisler result on uniformization of quasi arcs. Okay, so in this sense, this is a generalization of the Tokyo-Weisler result. Okay, so well, now the question is like, okay, can we do better? Okay, so obviously, so we say here, okay, the quasi-conformal tree is quasi-symmetrically equivalent to a geodesic tree, but can we get like one standard space? Okay, so obviously, like you have many different trees that are, not homomorphic, different topological classes. And so, in order to ask whether we have quasi-symmetric equivalent to one standard space, okay, well, we have to, we have to have more assumptions. All right, and so here is our model space, which we call the continuum self-similar tree, abbreviated CSST. And so what do we do? Okay, so we take here some line segment, okay, and then we divide it into two, and we attach one line segment of half the size. And now we keep doing this, okay? So each one we divide in the middle, and we attach a line segment of half the size. And we keep doing this, and we take the limit, okay? And the limit is what we call the continuum self-similar tree. Here in this picture, I sort of embedded this in the plane. In a sense, it doesn't really matter. So you can embed it in the plane, but you can also think of this as an abstract metric space. And if you want, you can, so, this picture here, so the way we embedded this thing is kind of self-similar. So if you blow this part here up by a factor of 2, you get the whole thing. And so it contains of these 3 parts that are, scaled copies of the whole thing. These 2 parts, actually, you have to flip over. Again, it doesn't really matter, but here are the self-similarities. So one way of defining the CSST is that it is the attractor of the iterated function system of these 3 maps. Again, the precise definition is not really that important. But maybe just when we have this here in the plane, we have 2 ways of assigning a metric to it. One is, of course, we can just give the metric from the complex plane, okay? Or a second way is, so when you have any 2 points, okay, you can look at the unique arc between these 2 points, and it in fact turns out that this arc is rectifiable, and you can actually assign a geodesic metric to this tree. And it turns out then that this geodesic metric is by Lipschitz to the metric from the plane. So you can either think of it as a metric from the plane, or you can think of it that it's a geodesic space, and these 2 metrics are by Lipschitz equivalent. Any questions? All right, so well, it turns out that this this tree has what we call uniformly dense branch points. And so, well, I have to say this. Okay, so we have here our tree. Okay, so, well, that's part of a tree, and now I have a branch point. And some part of the tree is attached to this branch point. And of course, if I, remove this point, I have 2 components that are large and 1 component that is not so large, and I just say that the height of this branch point is the size of this. Okay, so it's the size of the third biggest component. Okay, so again, I have this branch point, okay, and I look at the components that I get when I remove this point, and I order them by size, okay, and I look at the diameter of the third biggest component, again, because I kind of don't want to consider this size here and this size here, okay, and that I say is the height of this branch point, okay, and that I consider to be sort of how big the branching at this point is. Okay, and so now I say that branch points are uniformly relatively separated, okay, if I have two of these branch points, so I have here two branch points, let's say P and Q, okay, and so, well, what cannot happen is I cannot have two branch points that are close together where the branching is very, very large. So if they're close together, okay, then one of them has to be small, and if they get closer and closer together, they have to get smaller and smaller. Okay, so basically the big branch points where you have big trees kind of growing out, they are separated. Okay, so they sort of repel each other. Okay, and the second is sort of in the opposite way. Okay, so this means like the branch points are not too close to each other. Okay, and the second property is the other way around, that the branch points are not too far away from each other. Okay, so I have 2 points here, let's say A and B. B. Come on, A and B. Okay, and somewhere between them, I have to have a branch point where the branching is sort of comparable to the distance of these 2 points. So I cannot have A and B, and okay, there may be a lot of branch points, but all the branching is very tiny. So one branch point has to be big, okay, and that's what this property says. Okay, so we have distinct points, and then on the arc there is a branch point that is relatively big. Oh, and maybe I should say here, this notation means there is some uniform constant that I the constant is sort of hidden in the notation. And okay, and I call the tree uniformly branching is if both of these properties are satisfied. So the branch points are not too close together, but they're also not too far apart, too rare. Okay, and then I call the tree uniformly branching. Okay, so here is here's one theorem. So so we have a metric space, okay, and then it is quasi-symmetrically equivalent to the CSST if and only if so it is a quasi-conformal tree, doubling and bounded turning. It is uniformly branching, and each branch point has degree 3. So for the CSST, each branch point has degree 3. So if I take it out, we have 3 components. So obviously, if you have a tree where the branch point has degree 4, then it is topologically different from the CSST. So that is, it's a topological necessity. Okay, so we have this characterization of these trees. And here's a corollary. So when we have 2 uniformly branching quasi-conformal trees, each branch point has degree 3, then there are in fact quasi-symmetrically equivalent. Are there some questions for this so far? Okay, so I hope you guys are still here. Is anybody? I'm worried that my internet connection broke down and I'm just speaking to an empty room.
Oh, yeah, everything is fine.
Oh, okay, good. All right, because in the beginning it said my internet is unstable.
Yeah.
Okay. All right. So, well, and while we were kind of proving this, I actually noticed that we were always using the same strategy for proving quasi-symmetry. And so then we started to sort of formalize a strategy that we, in fact, are using to prove quasi-symmetry. And that's really what I want to do now, rather than, giving specific, specific things about, the previous result. Okay, and that's so the first thing is what I call visual approximation. Okay, and so note many self-similar fractals have natural decompositions in sets of geometrically decreasing size. Okay, so for example, let's say we have here the Sierpinski carpet. Okay, and so here are some iterations of the Sierpinski carpet. So at the, let's say, nth level, we have squares. Squares of side length 3 to the minus n, right? So we have natural decompositions in squares of the size, okay? And so, well, and let's say in general, let's say we have a metric space, okay? And now we have a sequence of finite covers of this metric space. Okay, and we assume that each set in the nth cover has diameter lambda to the minus n. And so here again, I sort of hide some multiplicative constants. So bounded above and below by constant times lambda to the minus n. Okay, so that's one thing, and that's exactly what we have. Let's say here for the Sierpinski carpet, or let's say for the Cantor set or the Sierpinski gasket, and so on. But we also want to have a bound in the other direction. So when we have two such sets in the cover, in the nth cover, and they are disjoint, then their distance should also be bounded below by this lambda to the minus n. Okay, so any set on the nth level has diameter roughly lambda to the minus n, and disjoint sets are separated by lambda to the minus n. Okay, and so if I have that, then I call the sequence a visual approximation of my space. Okay, and in fact here maybe just to remark this, so every doubling connected metric space has a visual approximation. That's not completely obvious because you also want to have the lower bound. In fact, you can get away with less than connected. Uniformly perfectness is all right, but let's just stick to connected because I guess that's easier to understand here. All right, so well, let me kind of go back to what I had in the beginning, okay, when I talked about these visual spheres or these metric spheres that are associated to certain Thurston maps. So here's a definition. So we have a Thurston map is just a map from the sphere to itself. It's a branch cover, which means in local coordinates you can always write it z to the d in local coordinates in around a point in domain and range, okay? And it is post-critically finite. So we take the set of all critical points, so critical points where the degree would be bigger than 1 or at least 2. Okay, so we take the set of all critical points and we take the forward orbit, and that is the set of critical points, and we assume that this is in fact a finite set. Okay, so that is a Thurston map. And okay, so before we had this, we had this the sequence of approximations that we call visual approximation. Okay, but now we want these approximations to have something to do with our dynamical system, meaning with our map. Okay, so that means we start with a finite cover. Okay, and then we take the pre-image cover by the nth iterate. So I didn't write down a formal definition. So really, okay, so really what you do is you take the sets here, you take the interiors, you take the pre-images, you take the components, and you take the closures, and that's what these sets are. But really, you think of xn to be the pre-images of my given finite cover by the nth iterate. And putting it another way, so we have this cover, and then the image is the finite cover that we started out with. Okay, and so if the mesh size, okay, so we take the maximal diameter of the set in the nth cover, if this goes to 0, then we say the map is expanding. And okay, so now we have a metric on the sphere, then we call such a metric visual, okay, if this approximation is a visual approximation with respect to my metric D. So again, so I have a metric D on the sphere, and we say this metric is visual if the set of covers that I obtain in this form is visual with respect to this metric D. So what does it mean? It means all these sets in the nth approximation have roughly the same size, namely lambda to the minus n. So they're all geometrically, they have the same size and they're all separate. So basically, these they satisfy these two properties. So basically, all the sets have the same size on the nth level. All right, so let's see, how am I doing on time? Okay. All right. So here is well, maybe just like a result here. So okay, so so the question is like, okay, do we have visual metrics for such Thurston maps? And the answer is, so there is a number, and you can compute it, but I don't want to give the definition here. And this number tells you what parameters are allowed for this visual metric. And conversely, so if you have a number that is between 1 and this lambda naught, okay, then you have a visual metric. Okay, so basically the set of visual metrics is some interval, okay, with this expansion factor. And in fact, you can choose this this metric in such a way that the map is expanding by a constant factor, and the factor is just this lambda. Okay, so what does it mean? Okay, so we have, for any point on the sphere, we can find a neighborhood such that in this neighborhood, the map expands by this factor lambda. So this is like the difference quotient. Okay, but you should note here, we don't take any limit. Okay, so on this small set, the map just expands by this constant factor. So the map is really just stretching by this factor lambda. Another way of viewing this is that equipped with this metric, the map is conformal. We don't have any distortion. In my neighborhood, the map just expands by this constant factor. There's no distortion whatsoever. Okay. Maybe just real quick. So visual metrics are not unique, but if you have two different visual metrics, then they are what is called snowflake equivalent. So you take one if you take some power of the other one, and then this is by Lipschitz to the other one. Okay. Questions? Oops. And here's maybe the result that I was alluding to earlier. Okay, so if you have a visual metric for an expanding Thurston map, then the geometry of this visual metric encodes properties of this map. Okay, so I have my expanding Thurston map, and I have any visual metric, and I have the sphere equipped with this metric, okay? And then the sphere, or the space, is quasi-symmetrically equivalent to the standard sphere, so it's a quasi-sphere, if and only if the map is topologically conjugate to a rational map. Okay, so this is very similar to Thurston's theorem. So you have like a geometric property when the map is conjugate. If you want, you can also write equivalent here to the rational map, namely that the sphere equipped with this visual metric is a quasi-sphere. Here's something else. So if the map is snowflake equivalent, so you raise it to some power, and then it's by Lipschitz to the standard sphere, if and only if the map is a lattice map. And there's more stuff that you can say here. Maybe I won't go over this in detail. All right, so to sort of explain this, let me kind of show you one example. Okay, so here is a Thurston map. And so, I mean, the Thurston map has been sort of chosen to generate a fractal sphere. And so that's really how you should think about this visual sphere. Okay, so what do? Is so I take a pillow, which is I take two unit squares and glue them together along a boundary. And then, you know, I have this the space, which is topologically a sphere. Okay. And now I have some sort of polyhedral surface which consists of small squares. So in this case, there are 10 little squares. Okay. And now I can define a map from this polyhedral surface to this polyhedral surface. So I take this square. Okay, and I just scale this by a factor of 2 and map it to this square, and then I extend by Schwarz reflection. So this thing is again scaled by a factor of 2, and then it's sort of mapped to the back, and so on. Okay, well, so now I guess this is like, well, I think several people here have sort of said that a Thurston map should be viewed as well, when you have two maps, and I think this is also what you should think here. So you have one map, which is the covering map, and well, and now you have two different kind of spaces, you know. So here is this pillow, and here's this other polyhedral surface. And in order to have a Thurston map, you have to identify this space to this space. So in a sense, there's this second map, which is this inclusion map. Okay, and so basically, you have to sort of map this polyhedral surface to this polyhedral surface. And the easiest is sort of to kind of push this thing that sticks out back here. And that's sort of what this picture here does. So I have sort of, you know, I mean, this this set is really the image of this set. And so, you know, this point is this point here, and so on. So it's still a quadrilateral, so it has 4 vertices. These are just sort of squished down, and then there's, you know, some face here on the back, okay, and the image is this space. So I guess I don't have that much time, but okay. And so, all right, and so now, well, again, I can have these two different points of view. One is that I have these two maps. One is this covering map, and one is this inclusion map. Or I sort of you know, make this inclusion map here, where this map is mapped to the same space as this, and then I have a self map from the same space to itself. This map is in fact obstructed, but let's not worry about this here. But one way how I can think about this is I have this polyhedral structure, and I pull back this polyhedral structure with F, and I get another polyhedral surface, okay? And I can sort of iterate that. So this space here, this square here, was mapped to this, okay? But now, you know, I sort of replace the square by this top here, and when I pull it back, I get another little flap here. So here is sort of the same picture, but I mean, so this picture was sort of made so that you see that this is a topological sphere. So this is like a little envelope, so you can put your hand inside. When I give these talks in person, I usually have some paper models, but for now you have to sort of believe me when I draw here on these things. Here I sort of made this a little less fancy because well, I want to iterate that, and then it becomes kind of difficult. Okay, so here's my first iterate, and okay, so now I take the second iterate, or the second pre-image of my pillow by this map, okay? And so basically, you know, like this square here got replaced by sort of this generator, or the same picture I had before, and this here again. And so this here was black, so this got mapped to the bottom. So, you know, there was nothing sticking out at the bottom, but we still divide it into 4 pieces. And then we iterate this, okay? So one way how we can see this is sort of, I mean, I call these sort of metric spheres kind of snowballs, because they're sort of higher dimensional analogs of the snowflake curve. So for the snowflake, I have an interval, and it gets replaced by some line segment or several line segments. And here I have a square, and it gets replaced by several squares, and then I iterate that. And so if you, let's see, I'm a little short of time. Okay, so if you iterate that, so you know, in the nth level, you get a polyhedral surface, okay, consisting of squares of side length 2 to the minus n. So each such surface has just a path metric as its polyhedral surface, okay, and you can really, so the limit of these surfaces in a certain way, in the Gromov-Hausdorff sense, that is exactly what the visual sphere for the Thurston map would look like. So basically, you know, you go to the limit, and then, you know, it's not just, you know, these squares, but it's sort of this fractal thing, okay? And then the map is nothing else that takes, let's say, one such things, one such fractal space, scales it by a factor of 2 and maps it to the whole thing. And that is exactly how these visual spheres look like. So one way of thinking about this is, so the map becomes very easy with respect to this visual metric. So the map just expands by a constant factor. The space becomes very complicated. So when you think about the typical setting of complex analysis, where you have, let's say, a rational map, so the Riemann sphere is a very, you know, nice, smooth object, but the map is sort of complicated, you know, in different places, the expansion is very different. Here, this is sort of reversed. The space becomes complicated, it's this fractal sphere, but the map becomes very easy. It only stretches by this constant factor 2, okay? And so, so you can think of that the map from this fractal sphere is conformal in a certain way. Okay. All right. So maybe let me just. No. Yeah, come on. Okay. So let me just indicate here one direction of this theorem. So we have this theorem. So this metric sphere was a quasi-sphere, if and only if the map is rational. And so let me kind of prove this implication. How does it go? Okay, so so this is a quasi-sphere. So there is a quasi-symmetric map from this space to the standard Riemann sphere, equipped, let's say, with a column metric or spherical metric, right? And so now we define a map here. So basically, we have this commutative diagram, and if we go up here, we get our map G. And so now what we get here, and we can iterate that. So then the nth iterate is, you know, we get the n here, okay? And so this map, and we also get this here in this diagram, okay? And so this map here is really conformal, right? I mean, the distortion is 1, right? So if you go here, 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 the distortion is bounded. So the distortion is given the distortion of this map, which is a quasi-symmetric map, and the distortion of this map, and the distortion, and there's no distortion happening here. So what does that mean? So this map here is uniformly quasi-regular, and therefore it's conjugate to a rational map by some standard results. So I'm out of time, so I don't know. Should I talk for 5 minutes or should I stop here? It's a little up to you guys.
You have more 2, 3, 4 minutes.
Oh, okay. So maybe I'll say a little. All right. So so we talked about these visual approximations. Okay. For our purposes, that's a little too restrictive. Okay. So what does that mean? So it means, well, if you have a quasi-symmetric map, then the image of a visual approximation will not be a visual approximation anymore, but the image will be what I call a quasi-visual approximation. And here, let me give a definition. Okay, so what is going on? So again, we have a metric space, okay, and we have a sequence of finite covers. They can be open, they can be closed. I don't really care, okay? And so, all right, and so now if I am, so here's my space, and I have this sort of sequence of approximations of my space, okay? And so, all right, so now if I am at the nth level and I have two sets, let's say X and Y, okay? And these two sets intersect, okay? So they sort of approximate or describe the same part of the space, then the diameter is comparable by some uniform constant. Here again, I'm hiding multiplicative constants in the notation, okay? So if you have two sets on the same level, the nth level, and they intersect, then the diameters are comparable, okay? And here's the second property. So if they do not intersect, then they are so they're disjoint, okay? Then the distance between these two things is bounded by the diameter of one of these two sets, okay? So again, we have two sets on the nth level, and they are disjoint, and the distance between is given by the diameter of one of these sets, okay? All right, and so now we ask ourselves, okay, what happens when I go from the nth level to the n+1th level? Okay, so here's some set nx on the nth level, and I have, oh, it should be, typically it will be small. I have another set x prime, okay? And these two sets intersect, so they sort of describe the same part of the space. Then the diameter cannot change much, okay? So the diameter of this set and this other set is comparable. So if you go one level down, the sizes do not change. All right, and so, well, and here's the last property that's maybe the, I don't know, least intuitive, but that's basically, well, at some point, we want our approximation to get small. The sets will get small. So we have here one set X on the nth level, okay? And so, well, we don't know, but there is some fixed number that is called K0. And if we go this many levels down, okay, then the size of this set here, X prime, decreases by some fixed factor lambda that is less than 1. Okay, so, you know, like if we go just some levels, you know, the sizes are roughly the same, but if we go nth, K0 levels, right, then the size decreases definitely by a factor less than 1, okay? And so this is what I call a quasi-visual approximation, well, all these four properties of a space, okay? All right, and so what does this have to do with quasi-symmetry? So here's a proposition. So we have two metrics on a space, okay? And we have a quasi-visual approximation with respect to the first metric, okay? All right, and so then the two metrics are quasi-symmetrically equivalent, okay? So I have just the identity with respect to the first metric and with respect to the second metric is a quasi-symmetry if and only if this approximation is a quasi-visual approximation with respect to the second metric, okay? And I mean, well, really what happened was, you know, by now I have proved, I don't know, 10 times over that something is a quasi-symmetric. And in fact, in a sense, I was really always using this theorem. In a sense, it's sort of not really new, but we sort of worked out the details. I should say, I mean, Kigami and Carrasco, they have similar ways of approximating metric spaces, and they have similar. They don't have this result, and they don't have the same setup as us, but they have similar things. Okay, so let's see. Should I stop here, or should I give you two more slides? What is
Yeah, stop here, please.
Okay. So, right, and so, yeah, so, I mean, the next slide would actually be to prove the other direction. But basically, you know, then you prove that if the map is a rational map, then, you know, the approximation that is induced by the map is in fact then quasi-visual, and that's how you prove the quasi-symmetry. Yeah, sorry, I'm out of time, so I stop you. Thank you.
Questions and comments from audience host? Okay, Alec.
So in your talk, you gave a very beautiful characterization of uniformly branching trees in terms up to quasi-symmetric equivalence.
Right, yeah.
Is there an analog of the statement for two trees where you may expect quasiconformal equivalence? And in my humble opinion, quasiconformal equivalence is more natural than quasi-symmetric equivalence of metric spaces.
So you talk about, so what do you mean? So you have like trees that are embedded in the plane, or you want?
Yes.
So you want, okay, so you want to have, okay, so you have two trees in the plane and you ask whether there's a quasi-conformal map of the plane that maps one tree to the other.
Precisely.
I mean, in a sense, I think this should work. And I mean, you know, there are related results. So there are, I mean, so for example, there is a result, I forgot by whom, but if you have a quasi Cantor set in the plane, then it is in fact, you know, quasi-conformally by a map of the plane where you map, you know, one Cantor set to the standard Cantor set. And I mean, of course, there is like, you know, I think this is due to alphas already, you know, you have a quasi-circle, then, you know, you have a quasi-conformal map of the whole. So in a sense, I think this should be possible to do, but I cannot say that I have done and nobody, I think it would work, but well, would require some work. At this, I would say I would be optimistic. You probably have to be a little careful. I guess you get topological problems, right? So you can have a tree, and so, you know, let's say you can always, you know, let's say flip around in which direction the branching occurs, and then you can, maybe you have to have, I mean, I think something would work, but it's not clear whether you have, you know, additional conditions. Yeah.
Thanks. More questions, comments from online participants? If not, thanks. Let's thanks to speaker again.